My name is Talora Ganaway. I am one Spanish class away from officially graduating from FSU in the computer science department, and I am the youngest of 4 sisters. For my presentation, I will be talking about artificial neural networks and how they use the backpropagation algorithm to learn. This presentation will cover some brief history about neural networks and backpropagation, a little bit of math about the backpropagation algorithm, some ideas about what neural networks can do, which is ponder and be afraid, a quick example about those ideas, and a little slide with links to resources that I used for this presentation. Alright, so we're starting with the brief historical review. Very, very brief. Basically, we want to know who did what. In 1943, Matthew McCullough and Walter Pitts published a paper about neural networks and how you can model the neural network of the human brain with circuitry. In 1959, Bernard Widrow and Marcian Hoff took the concepts of the paper by Cullough and Pitts and made Adeline and Madeline, which take advantage of adaptive linear elements. Madeline is actually used still today for noise filtering on telephone lines. Paul Werbos is credited with backpropagation from 1974, though the algorithm did not gain much attention and it did not get used widely until the 1980s. Next, we have mathematical torture on backpropagation. It's really not all that terrible. Each equation used to manipulate the data must be differential, as these are used to adjust the weights, and you cannot do that with imaginary values. Lastly, the thing you are trying to teach this network, or the prediction you are trying to achieve, must be deterministic, which means outcomes need to be reasonably predictable based on past observations. Next up, the multi-layer design of a neural network. We start with a single input layer instantiated with the original input data values. Next, we have one or more hidden layers which manipulate these values using nonlinear differential equations and spit a singular value to the single output layer. Once the output has the data, it can compare the calculated value with the expected value, which determines what step to take next according to the algorithm. Here we can see a pictorial representation of the layers. So you can see input is labeled X, output is labeled Y, and there are 3 hidden layers in this photo, all of which are labeled f of E, where E is the sum of products and f is some function. Backpropagation functions in 2 phases. Phase 1 is propagation, where it is split into 2 different parts. Part 1 is forward propagation, where it generates that first output. Part 2 is backward propagation, which takes the calculated error based on the output desired and the output obtained, and calculates the individual error for each individual node in the entire system. Phase 2 updates the weights associated between each node using the error from Phase 1, the partial derivative of the functions in each hidden layer, and something called the learning ratio, which we will show you. Once all the weights have been recalculated, the entire process restarts. The algorithm loops until the error is acceptable, which means the final output is close enough to the desired output, or until some other constraint is met. Here is a simplistic view of a 3-layered neural network with only 2 inputs and only 1 hidden layer node. As mentioned previously, X is the input, F is the function, and E is the sum of products from the input associated with those arrows going into that specific node. As depicted here, each hidden node manipulates its input with a nonlinear differentiable function. A common choice is the sigmoid function, which is f of x is 1 over 1 plus e to the negative x, where e is the natural number. It should be noted that in the pictures, e is not the natural number, e is the sum of products. Now we may enter phase 1, part 1, forward propagation. As you can see from the highlighted arrows, it starts with transferring the sum of products of the input, and then continues on with the sum of products based on the output of the hidden layer and the weights associated with the arrows. Finally, it reaches the final hidden layer and transfers to output, which will calculate what is called the error ratio. In this example, lowercase delta is the error and z is the desired value. We will then take that value and start phase 1, part 2. As you can see in this image, backward propagation takes that initial delta and calculates the delta for each individual node using the predetermined weight. This will show how much each node affects the final output, which is also known as the butterfly effect. We can now go into phase 2, but we are not going to step through the entire process all over again, going into every node. Basically, you can see that we are recalculating the weight using the old known weight, the error that we calculated from phase 1, the derivative of the function associated with the node that the weight is feeding into, and that fancy in symbol, which is the Greek lowercase eta. That is the learning ratio. Basically, what that one does is control how the system learns with an inverse relationship between speed and accuracy. Now that we have a basic understanding of how the backpropagation algorithm works in a neural network, we can think about the implications. Where are neural networks which learn through backpropagation currently used? Whether forecast research, artificial intelligence, and any general predictive experimentation, for example, a statistical prediction of cancer rates. You could probably use a neural network for that with enough data. Neural networks are still not very close to human functionality, but chaos theory could change that. So let's get into chaos theory for a little bit. First, we're going to define chaos. Edward Lorenz provides a fantastic definition quoted below from the Wikipedia page. He says, chaos is when the present determines the future, but the approximate present does not approximately determine the future. It should be noted that chaos is distinguishable from randomness. The butterfly effect is directly associated with chaos theory. It's basically high sensitivity to initial conditions, which, as we've seen with the backpropagation algorithm, is exactly what happens. Computer science has actually used chaos theory in certain areas before, such as cryptography and walking robots. However, it is considered new for neural network research. Chaos is naturally occurring, both in weather and in human brains. On the weather side, we've already mentioned forecasting applications for neural networks with backpropagation, and in fact there is a study that shows that this could be a viable substitute for current weather prediction software. Brains were a bit of a conundrum for scientists for a little while. It was observed that humans never reach an equilibrium state on the microscopic or macroscopic level. So what this ends up meaning is there's no warm-up time from rest and no cool-down time from activity. It's instantaneous information retrieval. We are always on standby to use our senses and to use our brains, which makes a whole lot of sense if you think about it, because when are we not using our brains? Here are a couple of quotes from a very informative paper on the importance of chaos theory. There's a researcher, Dr. Freeman, who believes that systems that settle into equilibrium or low-level oscillation states rather than wells of chaotic activity are doomed to failure. They make the analogy to biological neural systems in which these non-chaotic behaviors are indicative of coma, seizure, or death. The author continues on in the conclusion of his paper to say that some of the beneficial behaviors we could expect from such systems are selective memorization, faster pattern recognition, recognition of new patterns as such, and the development of new categories for these new patterns, and the ability to better distinguish patterns from background noise. I'd like to touch on a very quick example on how realistically we can portray these ideas in science fiction. This is from a popular video game trilogy called Mass Effect. There's a race called the Geth. They were created to help with simple tasks, so manual labor, things that required time but not skill. Eventually, the Geth were upgraded so that they could deal with more complex activities, and they share a knowledge system. So if one Geth learned that one process was not as efficient as another, that information would propagate throughout the entire network of connected Geth, and each new Geth created and connected to the network would have all prior information on that network. This is comparable to some of the technology today. In separate areas, however, they're not all combined into one place. So we have mass production machinery in factories, which complete menial labor. We have upgraded software and hardware that can do our laundry, our dishes, navigation, park cars, vacuum the floors without It is a sum of all knowledge, as well as something that you can connect to locally or universally. And the learning capabilities, we've got our neural networks. All of this put together can seem extremely scary when you think about it. Most science fiction does not put artificial intelligence in a particularly heavenly light. Mostly it's one day they're going to take over because our emotions are such useless things that the robots cannot understand how we are so incredibly inefficient. However, overall, neural networks, backpropagation, everything was so interesting to research and read about, and it just kept expanding into more and more fields, and that's what I really like to see when I research something about computer science, is cooperation with other disciplines. So I had a whole lot of fun with this, and it's made quite a few fantastic ideas more realistic for me. So I'm very excited to see where it goes from here.